And welcome again. We are going to solve another problem, and that is something else called the current through the capacitor. And the problem is the plates of a spherical capacitor, okay, have radii r and 3r, 3r. Okay. The spheres are short circuited, and the larger sphere is grounded. A point charge q is moved radially outwards between the two metal spheres with a constant velocity v. What current flows in the wire connecting the spheres when the moving charge is exactly halfway at a distance 2r from the centers of the spheres? Okay. Ignore the electrostatic field of the short circuiting wire. Well, it's a good problem. The difficulty of the problem lies in the fact that the originally existing spherical symmetry of the metal balls is spoiled by the presence of the point charge q, and because of this, the charge distribution on the spheres becomes highly inhomogeneous. Well, it becomes highly inhomogeneous, and the structure of the electric field is quite complicated. Fortunately, the determination of the charge distribution can be avoided, as we will see in the solution we are going to do. So, take an instantaneous moment, an arbitrary moment, and let us denote the instantaneous charge on the small sphere by q1 and the larger sphere by q2, and the instantaneous distance of the point charge from the center of the sphere as r, small r. So we know that since we have the information, or it is known that the potential of a uniformly charged spherical cell can be calculated outside as if charge of the sphere were concentrated at its center, and inside as if it were the same on the surface of the sphere. Therefore, the potential of the outermost, this one, grounded surface of the sphere can be obtained as the sum of potential of the three spherical cells. I would like to consider it this charge q also distributed on a concentric sphere, and there is nothing wrong in it because we are going to avoid the distribution of charges. And so this outermost sphere is grounded, so its potential will be equal to 0, and we can write simply the potential equation as due to q1 it will become kq1 by 3r. Due to charge q, it will become also just outside the surface of the grounded sphere as kq upon 3r, and due to charge q2 also as kq2 by 3r, and that becomes equal to 0. And this says nothing but q1 plus q plus q2 is equal to 0. Suppose this is our equation 1, and we need to find one more equation, and that can be found if we write the equation for potential at the common center of spheres. and this potential can be simply written as, due to q1 it can be written as kq1 by r, and due to q this is kq upon small r, and due to q2 that will become kq2 by 3r, and it is also equal to 0 because it is also grounded. And now we can find, using these two equations 1 and 2, we can find q1, and q1 will come in terms of radius small r, and you can see, you can find it will come to you like 3r by 2r minus half q. This is q1. And now to find the current, you can simply calculate current as I equals dq1 by dt. This is often called the equation of continuity, and you can also write it dq1 by dr multiplied by dr by dt, that is v, and so your result will become v dq1 upon dt. And after differentiating, you will get the result simply as 3 by 2 q v r by r square, and its direction, since you will get a negative value here, so its direction of the direction of current points towards the smallest sphere, though we need to find the value of current only. So, and at the moment when a small r is equal to 2r, so if you write the value of a small r equals 2r in this obtained equation, you are going to get the current that will become 3 by 8 qv upon r, and that is dimensionally correct, and this is your result. Thank you very much for watching.